Welcome back. In the first chapter we had looked at how we can create an open AI environment and how we can train a model on it and let it play. It worked, it just didn't perform very well. You might remember that we hit something like 1 brick per game, which is, compared to a human player, really bad. How we can enhance this, the first thing we are going to do in the 2.1 code base is add a bunch of environments. So let's not play one game at a time when training the model, but let the model train on 8 games in parallel. And for that we use this utility function make_vec environment. Before we used gym.make, and this utility function is just a nice way of creating a vectorized environment. So create 8 breakout games at the same time, put them into this wrapper class, this one we already had before. It basically makes sure that once the ball is dropped, the game sets done to true. So it basically knows when the game is over. The rest is very similar. Here we define the model that we want to have. We define the number of time steps and we tell it how to call it. So let's take something like 1,000,000 time steps so we have some chance of finishing today, and let's train the model. As we can see, we now hit something like 7 bricks per episode. When we look at the tensor board, we see it kind of evens out at 7 to 8 after 300,000 steps. So there's no real progress in the training after that point. It still far outperforms the one environment model. So we see kind of going from 1 to 8 really improves the rate of learning, and also, well, where we seem to be evening out. Let's take a step back to how the model interacts with the environment. The model comes up with an action, which is then fed into the environment using the environment.step. The environment comes up with a new state and hands back the observation to the model, which in turn takes the observation and predicts the next best action. In the beginning, we have executed this one by one in a for loop. Later, we trained a model to do that, and what the model basically, the training process basically did, is execute this thingy many, many times. I think we went for 1,000,000. So here in the model.learn, this circle was repeated over and over. Now, what we do in a callback is we just add a piece of code in here. So after the observation is calculated, after the environment has said, you have gone left, so now the ball flies in that direction, the callback is activated. And you can put either custom code into a callback, or you just use one of the pre-existing ones. And I want to mention the evaluation callback, which, well, lets you evaluate. So what happens is, instead of being executed every step 1,000,000 times, it's only executed every, well, nth step. You can define that. So let's say every 25,000th step, this one is executed. So 1,000,000 divided by 25,000 is something like 40-ish. So it gets executed 40 times. And it does basically the same. It has the action inside with the model predict. It creates a new observation, and the observation is fed back into the model. Now the difference is, here the model might be in a different state. You know, with the reinforcement learning models, your model sometimes takes bad or not optimal decisions just to explore stuff. You know, try new strategies, try new steps, try something it hasn't tried before. That you do in the learning phase, while in the evaluation phase it makes more sense to always take the optimal step. And also the environment might be different. So we have an evaluation environment in here. It can be the same, but you will actually get a warning if you use the same one. It should be compatible, so it should have the same shape, it should have the same observation space, the same action space. But it might be slightly different. So now we are in the file 2.2, and the beginning is the same. We have a bunch of environments, and the only thing I did is abstract away the creation of environments into a function because I need to do it twice. I do it once for the environment and once for the evaluation environment. And you see I choose a slightly different parameter. So we have 8 training environments and 2 evaluation environments. Here we define the callback. So I'm just taking an existing callback from the stable baselines called eval callback. I hand it over the evaluation environment and I tell it where to save the best model. So that's also a nice feature of the eval callback. Basically, it evaluates every 1,000, 25,000 or whatever I defined steps and then writes back the best model. So even if during the training the model gets worse at some point, I still have the best model saved. So this was the evaluation. I've implemented a custom callback, one that is also run at every step. And it is run on the same environment as the learning. So we have here the custom callback. And what it basically does, it saves some extra key metrics for TensorBoard, which I think I called something like custom cumulative score. I just wanted to check whether my understanding of what the reward system is and how it's saved and added up coincides with the way it's already implemented. So let's have a look at that code. You see here I'm importing the base callback and I let my callback inherit from the base callback class because I don't want to re-implement everything myself. I changed the init a bit, so I used the init function from the base callback, from the super of my callback is the base callback. And in addition to that init, I'm initializing 2 more variables, the cumulative reward and the cumulative done. It basically tells me how often did I hit a brick and how often did I finish a game. And then on each step, what should be done is the reward is the mean numpy mean of the rewards we have. It's the mean because we have several environments vectorized. You remember this number of environments up here. So for the training environment, it's 8. So the self.locals rewards is a vector of 8, and I'm taking the mean. So basically what I'm saving here is the average reward over all environments and the average number of times the game was finished. And then I'm just, for each step, I'm adding it up. So this function gets executed on each step of the environment, and I'm just accumulating, starting from 0, and then at the end I hopefully have all of the rewards that it has collected. And I'm logging that to the custom/cumulative reward. When we execute the model.learn, I'm adding those 2 callbacks as a list. And I'm basically telling it, well, use both callbacks. So let's run the model and see what comes out. Welcome back. There was a bit of an issue. The whole thing took much longer than expected. As I mentioned before, in an evaluation environment, the model will behave differently. And in this case, what happened is it would always take the action that had the highest score, the action that was most probable to have a good outcome. That usually should work good. The problem is here it brought the game into a state in which it was stuck. And you see that was the output. Evaluation number of time steps 80,000. So basically it was just bouncing the ball up and down. And would not kind of move the pedal around a bit once it got bored and try something new. So I could solve this by setting deterministic to false. That would not always take the best action, but it would just, well, throw a piece of dice with the probabilities, the scores assigned to the different actions. And with that, I was able to get some sensible results where the evaluation wouldn't be stuck for 80,000 time steps. So let's have a look at the tensor board. The first thing we see is now we got new values here in custom and in eval. Eval is from the evaluation callback and custom is from the custom callback where we added the cumulative done and cumulative reward. The other relevant piece is once we scroll down and look at rollout, so the values that are evaluated during the training phase. Let's remove the smoothing a bit and enlarge this graph of the average reward. Well, for one, you see that I took the old results and just trained them a bit longer beyond 200,000. I think we had initially for the whole length, so we can properly compare it. And you see that the blue and the red one actually give very similar results. That's to be expected because both are the same code base and the only difference are the callbacks, which in this case do not influence the training in any way. Now we can focus on creating a baseline model, a model that, let's say, performs well enough with some known well hyperparameters. And for that, we're just going to copy code from Stable Baselines3. So if you go to my GitHub, you go into the learning to_baseline folder, scroll a bit down. It will first give you the link to the zoo. I strongly recommend exploring that, especially exploring their documentation. The quick one is to install the requirements, to check out their Git repository, go into that folder, install the pip requirements, and then you can run this one command line to create a new model based on PPO for Breakout with 1 million steps with the seed logging to the tensor board. The light blue line are the results from the zoo code, and you see it outperforms our previous models by a bit. In order to really understand what's happening in that code, the way I tackled it is taking the command line parameters, copying them, go into Spider, open the train.py, the code from the zoo repository, and on run configuration per file, we run the file with custom configuration. And we say the command line options should be those. And now we can run the debugger and really follow through the code step by step. That is a bit tedious, but it really helps in understanding what is happening there. And to save us some time, let's stop that. Let's look at the 2.3 copying HP zoo. This is my understanding of what the zoo code does, and well, just removing a lot of the code that is not used for this particular environment and this particular model. Now, when we dive into the simplified version of the zoo code, in the beginning we find the different hyperparameters which were chosen for the model. In the section on the wrappers, you will find the Atari wrapper being used as well as the FrameStack one. And on both, you will find some information on the Stable Baselines documentation. The Atari wrapper basically includes a bunch of other wrappers, the clip reward, the episodic life, which we already had before, a bunch of others, and which I find notably is the warp frame wrapper, because it takes the 210 x 160 picture and scales it down to an 84 x 84 picture. Which makes sense, but it creates some issues down the road, which we will look at in the next chapter. Besides the Atari wrapper, we are using the FrameStack wrapper with a FrameStack of 4. And this means the model at each point when it needs to make a prediction does not only have the current state of the observation, it also has the other last 3 states. And can make a decision based on that. There's a different way to do this if you choose a model that looks at recurrence. So you will also find a comment here on the Stable Baselines documentation which mentions a recurrent version of PPO, but actually in the end they also recommend using the frame stack. It just makes life a bit simpler. You don't need to think about any recurrence of your model, and you still can have the model remember a bit of the past. This is especially relevant in Breakout because in Breakout the ball flies around, so it moves. And in order to derive something like a speed or a direction of movement, well, you can't only look at the current frame, you at least have to have the last frame as well. Now, after the wrappers, we have the definition of the evaluation callback, and after that we're going for the linear schedules, which is basically taking a hyperparameter and changing it over time. So when we go back to TensorBoard, let's collapse the custom and the evaluation and the rollout and look at the train. And here we will find two very straight lines. And this is because they're not kind of measurements of the environment, but they're hyperparameters. And these hyperparameters change with the progress of the model. And well, they're defined linearly in the number of time steps. So you see it going from the starting value down to 0 linearly. And this is basically what this function does. It takes the progress remaining, which is a float between 0 and 1, multiplies it with the initial value of the hyperparameter. And this is applied to the learning rate as well as the clip range. And after that, everything's as we expected. We have the model, which is defined now with a bunch of more hyperparameters. Then we train the model, and in the end, we save it. And this gives us a good overview of what the zoo code actually does. And it gives us a good starting point and a good baseline to develop better models. Now let's run it and look at the results. Now when we compare the results of the original zoo code to the simplified code I've just shown you, we see the results are in general very similar. We can believe it's kind of the same quality of model, it's the same type of baseline. I do not know why it doesn't give exactly the same results, because I do believe I have used the same seed and the same exact hyperparameters. So if you spot something where you say, this is it, this is why it doesn't behave exactly the same way, please either add a comment to this video or make a pull request on GitHub. But this will provide us with a good baseline for further progress. We have a piece of code which is short, which we well understand, and which gives us decent results. So now we can really get into optimizing our own model.